Hello. Hello. Good evening, everyone. I am Saurabh, and I welcome you to this session for the NPTEL course Applied Thermodynamics. In today's session, we will focus on steam power system. Okay, so we for last few weeks we have been discussing steam power systems. So we'll continue our discussion and we'll try to solve some problems. Okay, and this is our final session on steam power system. Okay, so from next week we will start internal combustion engines. Okay, so we will begin with question number one. Question number one says, in an impulse turbine, so there are four options. First, that steam is expanded both in fixed and moving blades continuously. Part B says steam is expanded in nozzles only and there is a pressure drop and heat drop. Last part C says steam is expanded in moving blades only. And last option says pressure and temperature of steam remains constant. Okay, so you have studied that there are two main types of turbines, impulse turbine and reaction turbine, right? Okay, so you have studied that in impulse turbine there is no enthalpy change in moving blades, right? So whatever enthalpy change takes place, that change happens in fixed blade. Okay, fixed blade is basically nozzle, right? So steam is expanded in nozzle only. Okay, and when steam expand in nozzle, so nozzle what basically nozzle do is it converts the mechanical energy to the kinetic energy. Okay, so on the expense of pressure and enthalpy, the kinetic energy is increased. Okay, so part B should be the correct option. Okay, steam is expanded in nozzle only and there is pressure drop and heat drop. Okay, and what we get stream at higher velocity at the exit. Okay, so we get a higher kinetic energy. Okay, so in nozzle, the nozzle neither consumes work, neither does it produce work. It just convert the mechanical energy to the kinetic energy. Okay, in case of steam it converts heat and pressure energy to the kinetic energy. Okay, I hope this is clear, and I will show you one diagram, simple diagram. So impulse turbine, there are two types of compounding: pressure compounding and velocity compounding. Here I have shown pressure compounding. Okay, so here you can observe that there are some moving blades and there are some nozzles. Okay, so for example, uh, here this is a nozzle. Okay, here this is a nozzle. Okay, and here this is a moving blade. Here this is a moving blade. Okay, so this is nozzle, this is a moving blade, and just below this diagram you can see more clearly. Okay, these are moving blades and there are some nozzles, then moving blades. So basically one pair of nozzle and moving blades forms one stage. Okay, so if there are more than one stages, so you will find more than one pairs of nozzle and moving blades. Okay, so there are pressure and velocity plots. Okay, so you can see that pressure drops only in the nozzle. Okay, in the first column you can see that pressure is dropping. Then in moving blades pressure is constant, right? Pressure is constant. Then again there is nozzle, so pressure is again, there is again a pressure drop. Okay, then in moving blade there is no pressure drop, again in nozzle there is a pressure drop, and in moving blade there is no pressure drop. Okay, so pressure drop takes place only in the nozzle. Okay, and velocity, you can see in nozzle velocity is increasing, kinetic energy is increasing because pressure energy is being converted into kinetic energy. Okay, and in moving blade velocity is decreasing. Okay, so to summarize we can say that pressure drop takes place only in nozzle. Okay, for impulse turbine. Okay, so there is this is a diagram for pressure compounding. There is one more compounding that we call velocity compounding. Okay, so what is velocity compounding, that I will encourage you to check and try to understand by yourself. So I hope this is clear. Now we will move to the question number 2. Okay, question number 2 says, in which turbine pressure energy of water is first converted into kinetic energy by means of nozzle kept too close to the runner. Okay, so it is just an another version of the previous question. I hope that you are able to answer this question, and the correct answer is option A, impulse turbine. In impulse turbine, pressure energy of water or steam is first converted to kinetic energy by the means of nozzle, right? And nozzle is kept close to the runner. Runner is basically moving blades. Okay, the correct option is impulse turbine. Okay, next question. Question number 3. Before going to question number 3, we will we should have just we should have a little discussion on nozzle. So as I told you that in nozzle there is no heat exchange and there is no work interaction. Okay, so you can use energy conservation. Okay, so whatever energy is coming, that the same amount of energy should go out. Okay, so if you try to write the energy conservation question, then you can neglect the potential energy changes, you can neglect the heat exchange, heat transfer, not neglect. Actually, there is the heat transfer should be zero in ideal case, and there is no work transfer. So whatever uh, enthalpy changes are there, that will appear in the form of increased kinetic energy. Okay, so nozzle basically increases the kinetic energy, and pressure and heat content is lost. I mean, it is reduced. And diffuser is just opposite of that. Okay, so now it will be easy for you to answer question number 3. In fluid dynamics, a diffuser is a device that is designed to slow down fluid flow and increase its static pressure. Slow down the fluid flow means decreases the kinetic energy, and it increases the static pressure. So is it true or false? So a nozzle basically reduces the pressure and it increases the fluid velocity. And diffuser is just opposite of that. So it increases the static pressure and it slows down the fluid flow. Okay, so this is a correct statement. Okay, so the answer should be part A, true, right? Okay, if there is no doubt, then we will move to the next question. Question number 4. Question number 4 says the degree of reaction of an impulse stage of a turbine is. So if you know what is degree of reaction, then you can easily answer this question. So degree of reaction is, what degree of reaction? So degree of reaction is the fraction of enthalpy change that takes place in rotor. Okay. So enthalpy change in rotor or moving blades divided by total enthalpy change. Okay. So this fraction is called degree of reaction. And you know that in case of an impulse turbine, enthalpy change in rotor is zero, right? Okay. So degree of reaction for an impulse turbine should be zero, right? Okay. So the correct option is last option, zero. Okay. If it is clear, then we can move to the next question. Question 5. Question 5 says, in economizer, feed water is preheat by using flue gases to improve overall efficiency. So you know what is an economizer? It is mounted at, just, top part of an boiler. And the purpose of economizer is to use the heat of, flue gases, because flue gases you will anyway throw into the environment, right? And those flue gases are quite hot and they have some heat energy. So if you can use that heat energy to preheat the water, the feed water that is going to the boiler, then you will utilize that heat of flue gases. So in this way you will improve the overall efficiency, right? How? Because first of all, the heat addition in the boiler that will take place at an elevated temperature, because you have preheated the water, right? You have preheated the feed water. Right? So instead of wasting the heat of flue gases, you are utilizing that heat. Okay, and this is done with the help of an economizer. So this statement is true. Okay, an economizer in economizer, feed water is heated by using flue gases to improve the overall efficiency, right? Because efficiency is just net work output divided by total heat input, and now the total heat input will be reduced because you are also utilizing the heat of flue gases. Okay, so we will see. If there is no doubt, then we will move to the next question, question number 6. Question number 6, it says that the condensation of steam in a condenser takes place at. So this is very, very easy question. Even without the knowledge of power plant or steam power plant, you can easily answer this question. Condensation is a phase change process. Okay, and phase change, from any phase change basically, it takes place at constant pressure and constant temperature, right? If you are keeping the pressure constant, then during the phase change process, if you are keeping the pressure constant, temperature will remain constant, and if you are keeping the temperature constant, pressure will remain constant. So basically, condensation is uh, phase change from vapor to liquid. This will take place at constant pressure and constant temperature. Similarly, the boiling process in the boiler, that will also happen at constant pressure, right? Because that is also a phase change process. Okay, and if you remember the TS diagram, then it will be even more easy. Okay, so 2 to 3, this is constant pressure heat addition in the boiler. Okay, and 3 to 4 is adiabatic expansion in turbine, and 4 to 1, this 4 to 1 condensation, this you can see it is happening at constant temperature. And if you try to draw a constant pressure line, it will look something like this. Okay, so in the dome region, the constant pressure and constant temperature lines will coincide. Okay, so condensation will take place at constant pressure and constant temperature in the saturation region, right? Okay, so we will move to the next question. Question 7, it is about Molière diagram. So you might have studied about Molière diagrams. These are very important when you are solving some numerical questions. Many times you'll have to refer Molière diagrams to get the properties of steam, right? So in a Molière diagram, constant pressure lines. So what happens to constant pressure lines? Do they diverge or converge, or they maintain equal distance, or they are just random? So if you have observed Molière diagram, you can easily answer this question. If not, I will show you a Molière diagram, then you will be able to solve this question easily. Okay, so here is one Molière diagram. So Molière diagram are basically, enthalpy entropy chart. Okay, so here you can say on x-axis there is entropy. Okay, and on y-axis there is enthalpy. Okay, this is enthalpy. So these green lines you can see, these are constant temperature lines. Okay, and these blue lines are constant pressure lines. Okay, and these red lines are basically quality of steam. Okay, so we have to focus on constant pressure lines. So if you move from left to right, so then the distance between two constant pressure line, is that increasing or decreasing? If you see very carefully, you can tell that it is increasing. So constant pressure lines are diverging. But if it is not very clear, then I will show you one more diagram, because in this diagram you can see that x-axis is starting from 5 and y-axis is starting from 2000. Okay, so this is some sort of, a cropped part, or some zoomed in part of some specific region in the Molière diagram, because this is, usual values which you often encounter. But if you see one full Molière diagram which starts from 0, then you will be easily able to answer this question. Okay, and this is the diagram, another diagram. So here you can see the values are starting from 0. Okay, so again these blue lines, I don't know whether it is visible. I will just zoom in for you. Okay, so these are blue lines. These are constant pressure lines. Okay, and you can see that all these lines are, very very confined in this region. Okay, so as you move forward towards right, these lines are diverging. Okay, so in this diagram it is, more clear. Constant pressure lines diverges. Okay, in the Molière diagram is basically HS diagram, right? So now it is clear. Okay, so we can answer our question. In Molière diagram, constant pressure lines diverge. Option B. Okay, I think we can move to the next question. Okay, if at inlet of the turbine. Water possesses kinetic energy as well as pressure energy. The turbine is known as reaction turbine. So I have to tell that whether this statement is true or false. Okay, so it is saying kinetic energy as well as pressure energy. Okay, so this means that there is some pressure energy, and that pressure energy will be, converted into mechanical work in the turbine blade, in the rotating blades. Okay, so there will be some enthalpy changes in the rotor. Okay, so definitely this is not an impulse turbine, right? Because in impulse turbine there is no enthalpy change in the rotor blades. So this turbine should be a reaction turbine. Okay, so it is saying reaction turbine. So yes, it is a true statement. Okay, so we will move to the next question. Question 9. Question number 9 says, superheating of steam in the boiler is done at constant volume, constant entropy, constant pressure, or constant temperature. So superheating. So superheating means you have already converted all the water into steam, and you have steam and you are, heating it more. Okay, so that is superheating. So this is not a phase change process. Okay, because you already have steam and you are just heating it. If it would have been a phase change process, then it will happen at constant pressure and constant temperature. But superheating, it is not a constant, it is not a phase change process. Okay, so to answer this question, we will make the TS diagram, then it would be easy. Okay, so from point 2 to 3. Okay, first of all, I will tell you that this is a constant pressure line as well. So 2 to 3, it is heat addition in boiler. But as you can see that at point 3 dash, you have got saturated steam, but you are still heating the saturated steam. So 3 dash to 3, this is superheating. Superheating. Okay, because at point 3 dash you have saturated steam. Okay, so this superheating, this coincide with a isobar. Isobar means constant pressure line. So this heat addition process, this takes place at constant pressure, and you can see that from 3 dash to point 3, temperature is increasing. So it is not a constant temperature process, it is a constant pressure process. But in between this dome, from 2 days to 3 days, it is constant pressure and constant temperature. But 3 days to 3, which we are calling superheating, their pressure is constant, but temperature increases. Okay. So last option should be the correct option. Constant pressure. Okay. I hope this is clear. We will move forward. Okay. We have question number 10. Question 10 says fire tube boilers and water tube boilers. So there are some low pressure boilers and some high pressure boilers. So either fire tube boilers are low pressure or high pressure, and water tube pressure are low pressure or high pressure. This we have to tell. So in we know that in boiler there is combustion is taking place. Okay, and the heat energy released during combustion that is transferred to the water. Okay, so there is heat transfer from fire to the water, and this for this heat transfer there should be some sort of arrangement for the heat transfer. For heat transfer, there are similar to heat exchanger. There in heat exchanger, there are some pipes, okay, some tubes. So same things are there in the boilers. There are some tubes. In tube there can be either water or fire. So the boilers in which water is flowing inside the tubes, those boilers we call water tube boilers. And the boilers where fire, the flue gases are flowing through the tubes, those type of boiler we call as fire tube boilers. Okay, I will show you the diagram. Okay, so here is the diagram. In the first diagram you can see these are fire tube boiler. So you can see that there is furnace. From furnace flue gases are going through the pipe. Okay, so flue gases are going through the pipe. Okay, water is not going through the pipe. So this is fire tube boiler. And the second part you can see that water is going through the pipe. Okay, so this is water tube boiler. Okay, so both of these boilers have some advantages and disadvantages. Okay, for example, fire tube boilers, these are simple and compact. These are efficient and they have low total cost of ownership. Okay, these fire tube boilers, simple and compact. Okay. They are efficient and they have low total cost of ownership. And these water tube boilers, in the water tube boilers, you can get high pressure and high temperature. Okay. Okay. They are more precise. Okay. But of course, these things will come at some cost, right? So if you want high pressure and high temperature rises, then you'll have to use water tube boilers. Okay. So I hope the difference between water tube and fire tube boilers is clear. So now you can answer this question. Fire tube boilers are, as we discussed, they operate at low pressure as compared to water tube boilers. Okay, and water tube boilers operate at higher pressure as compared to fire tube boilers. Okay, so fire tube boilers are sometimes called low pressure boilers, and water tube boilers are called high pressure boilers. Okay, so option A should be the correct option. Okay, so you can see in hot tube boilers, water is filled in some sort of tank, and you are getting some steam, but that steam is not at high pressure and high temperature. Okay, temperature can be high, but pressure will not be that high. And in water tube boiler, you can get higher pressure. And you know that during phase change process, if you increase the pressure, the temperature will increase. Okay, so if you want to get more temperature, you can increase the pressure. Okay, so I hope that this is clear, and we can move to the next question. Question number 11. It says in condenser, heat is dissipated mainly by, so there are certain modes of heat transfer: radiation, convection, conduction, or evaporation. So you know that in a steam power plant, there are four main components. The water is pumped to a boiler. Okay, and in boiler, heat is added at constant pressure, and 3 to 4 there is isentropic compression in turbine, sorry, isentropic expansion in turbine, and 4 to 1 there is heat rejection in the condenser. Okay, so heat is dissipated in condenser. So what is the mode of heat transfer? How the heat is dissipated? Is it because of radiation, or convection, or conduction, or evaporation? So one thing is quite obvious, that all of these modes will be there, but we have to tell which one is the dominant one, because whenever there is some temperature, at all the temperature radiation will take place. Okay, and whenever there is some contact, okay, so conduction will take place. Okay, and if there is some fluid, then there will be convection as well. But the dominant mode of heat transfer in the condenser, that we have to tell. The correct option here is convection. Okay, so condenser is some sort of heat exchanger, and some cold water goes in to condense the steam which is coming out from the turbine. Okay, so I will show you the diagram. Okay, so here is the steam power plant, and here is the condenser. You can see that steam, expanded steam, will come, and some hot water, sorry, some cold water will come inside. Cold water or any cold fluid, and it will leave as hot water, and your steam will be condensed, and here you will get water. Okay, So this heat exchanger, inside this condenser, what will happen? Convection will happen, right? Okay. So convection is the mode by which the heat dissipation takes place in the condenser. Okay. So if it is clear, then we will move to the next question. Question number 12. A steam nozzle converts. So we have been discussing nozzle. We have discussed nozzle in last many questions. So what does a nozzle do? So option A says that it converts heat energy to the kinetic energy, heat energy into potential energy, kinetic energy into potential energy into heat energy. In many previous questions, we have discussed this, that nozzle, it in nozzle there is no, heat exchange and there is no water interaction. So if you try to write the steady flow equation, a generalized equation, then it is something like this. Okay. So since in nozzle there is no, we can assume that potential energy changes are negligible. Okay, there is no heat exchange and there is no energy interaction. So we have left with this equation: h1 plus v1 square by 2 is equal to h2 plus v2 square by 2. And if you try to write it like h1 minus h2 is equal to v2 square minus v1 square by 2. And in nozzle, at the outlet you get higher velocity, and that is the purpose of a nozzle. So nozzle converts heat energy into kinetic energy. Okay, so the main purpose of nozzle is to increase the kinetic energy. So at the end, at the outlet, the velocities are quite high, and the inlet velocities can be neglected as compared to the outlet velocities. Okay, so you can also write it as h1 minus h2 is equal to v2 square by 2. We can neglect the v1, the inlet velocities, because they are very very small as compared to the outlet velocity. But anyway, the main purpose of nozzle is to increase the kinetic energy. Okay, so in steam nozzle, the heat energy is converted into kinetic energy. Okay, so this enthalpy change, this will appear as increase in kinetic energy. Okay. If it is clear, then we will move to the next question. Question 13. Question 13 says exergy analysis is based on second law of thermodynamics. Yes, it is. Second law of thermodynamics says that for an isolated system, there is always, increase in the entropy. Entropy that can remain constant, or it will increase for an isolated system. It cannot be decreased. Okay, so second law is in the terms of entropy, and exergy is, you know, just extension of that second law. Okay, and for the processes, exergy is, usually destroyed, right? So for an isolated system, exergy will be always, destroyed. It cannot increase. Okay, so it is based on second law of thermodynamics, and it tells that how much energy was available, and you know that available energy will always be reduced. Okay, so exergy is some sort of, potential to do some useful work. So we will move to the next question. Question number 14. It says that in an impulse turbine stage, the heat drop in fixed and moving blades are 30 kilojoule per kg and 40 kilojoule per kg. The degree of reaction for this stage is, so there is some enthalpy drop in fixed blade that is given to be 30 kilojoule per kg, and there is some enthalpy drop in rotor blade that is given to be 40 kilojoule per kg. So we have to tell the degree of reaction. Degree of reaction we have already discussed in some previous question, and it is the enthalpy drop in moving blades to the total enthalpy drop, right? So this fraction is called degree of reaction. Okay, so 40 kilojoule per kg divided by 40 plus 30 kilojoule per kg. 40 kilojoule per kg is enthalpy drop in rotor, and 40 plus 30, that is 70 kilojoule per kg, that is total enthalpy drop. Okay, so 4 by 7. So this is the degree of reaction. So is there any option? Yeah, sorry, option A. Option A should be the correct option, right? Hope this is clear. We will move to the next question, question 15. Question 15 says air at 100, sorry, 600 kilopascal and 500 Kelvin enters an adiabatic nozzle. Okay, so adiabatic nozzle means there is no, heat transfer between nozzle and environment. That has an inlet to exit area ratio of 2:1. Okay, so at inlet and at outlet, the ratio of area is 2:1 with the velocity of 120 meter per second and leaves with the velocity of 300 meter per second. So at inlet the velocity is v1 120 meter degrees 120 meter per second, and at outlet the velocity is 300 meter per second. We have to determine the exit temperature and the exit pressure of the air. Okay, so at inlet the properties are given. Okay, so as we have discussed in many previous questions, that nozzle there is no work transfer and there is no heat transfer. So whatever there is energy in, the same energy will go out. Okay, so this will be 0, right? So this means energy in is equal to energy out. So at inlet, what is the energy? If you try to write the energy, then at inlet, and we are assuming that, obviously there is mass conservation and other things. So mass flow rate is constant. Okay. So at inlet, energy will be m into h1 enthalpy plus v1 square by 2, and we are neglecting potential energy changes. Okay, is equal to m m dot. This is the mass flow rate, that is constant. H2 plus v2 square. Okay, and we have assumed potential energy changes to be potential energy changes neglected. Okay, and there is no heat and work transfer. Okay, and there is no change in mass flow rate, that is constant throughout. So what we have? We have h2 minus h1 is equal to v2 square minus v1 square by 2. Correct? So v1 we have, v2 we have, and enthalpy values we can find from the tables, steam tables, right? So enthalpy at you know inlet we can find from the steam table, and then we can calculate h2. H2 will be equal to h1 plus v2 square minus v1 square by 2. We have all these values, but for the h1 we'll have to check the steam tables. Okay, so not the steam table, sorry, this is air. So we'll have to check the table for properties of air. Okay, .500 Kelvin. Here is the 500 Kelvin. Enthalpy is 502.02. Okay, from air properties table we have H1, that is H at 500 Kelvin. This is 503.02 kilojoule per kg. Okay, so H1 we have. Now you can calculate H2. So H2 will be 503.02 plus V2 is how much? 380. 380 square minus 120 square, right? Okay, so this will be our H2. Okay, 03 plus 380 square minus 120 square divided by 2. So why we are getting this large value? I think there is some mistake. Yes, we will have to divide it by 1000, right? Okay, because this is an SI unit and we are writing in kilojoule per kg, right? Okay. And again, we have made one mistake here. There should be one negative sign. Okay, there should be one negative sign. This is 65 kilojoule per kg. Okay, so now we have H2 equal to 438.02 kilojoule per kg. Okay, and we have to tell the corresponding temperature. For that, again we can check the table, steam this air property table. So 438. So we will check at which point we are getting this value. So at 440 it is 441, and at 430 it is 431.43. Okay, so at some point it will be, you know, at 430 Kelvin, H is 431.43, and at 440 Kelvin we have H equal to 441.61 kilojoule per kg. Okay, so at some point in between this 430 and 440, we will find H equal to 438.02 kilojoule per kg. And to find that value, you can use interpolation. Okay, and I have the value, that value, and that is T2 is equal to 437 Kelvin. Okay, so at 437 Kelvin, the enthalpy will be approximately 438.02 kilojoule per kg. Okay, so that will be the temperature, outlet temperature. Okay, So what we had to find? We had to find exit temperature, so that we have got, and the exit pressure of the air. We have to find exit pressure. Okay. So to find the exit pressure, we can use the mass conservation, right? We can use PV is equal to nRT. Okay. From mass conservation, we can write it as rho 1, V1, A1. Rho is density, V is velocity, and A is the area of cross section, is equal to rho 2, V2, A2. Okay. A2 by A1 is given. Sorry, A1 by A2 is given. Okay. Velocities are also given. The only thing that we have to find is densities. Okay. And density is just the reciprocal of a specific volume. Okay. And that is equal to 1 by RT by P, right? Because from ideal gas equation, you have P is equal to RT. Correct. Okay. So now you can use the ideal gas equation and you get 1 by V1. V, this small v is specific volume and capital V is velocity. Okay. A1 V1 is equal to V2. From ideal gas equation, you have 1 by RT1 by P1 to A1 V1 is equal to 1 by RT2 by P2 A2 V2. Okay. From here you can write P2 is equal to A1 by A2, T2 by T1, V1 by V2 into P1. Okay. So now you have all these values, you just need to substitute. Okay. A2 by A1 we have, this is 2 by 1. T2 we have calculated and it is coming out to be 437, and T1 we had how much? 500 Kelvin, right? I'm not writing the units because anyway they will cancel out. Velocities also we have velocity at inlet as 120 and at outlet 380. And pressure at inlet was 600 kilopascal. Okay. So now we can find the P2. $37 to 120 into 600 divided by 500 into 380. Okay, so you are getting 331.2. Okay, so this will be the pressure at outlet. Okay, this is our answer. Okay, so we were given the velocity at inlet and outlet. We were given the ratio of area of inlet and outlet. We were given the inlet pressure and inlet temperature, and we were asked to find exit temperature and exit pressure. So in this case, we had to make the we had to make the use of air property tables. Okay. So in exam, either these tables are usually given or the values, required values at these points are given in the question itself. Okay. So I hope that this question is clear, and move to the next question. Question 16. It says that steam flows steadily through an adiabatic turbine. Again, this is adiabatic turbine, so there's no heat transfer between surrounding and the turbine. The inlet conditions of the steam are 4 megapascal, 500 degrees Celsius, and 80 meter per second. And exit conditions are 30 kilopascal, 92% quality, and 50 meter per second velocity. The mass flow rate of steam is 12 kilojoule, 12 kg per second. We have to find the change in kinetic energy, power output, and the turbine inlet area. Okay, so it is quite similar question. Okay, so but here it is steam, so we will have to use steam tables, not the air property tables. Okay, we have turbine. Okay, and the mass flow rate is 12 kilogram per second. Okay, at inlet conditions are given 4 megapascal, 500 degrees Celsius temperature. So 773 Kelvin. Velocity is given to be 80 meter per second. Okay, and at outlet pressure is 30 kilopascal. Okay, steam quality is 92%, and V2 is 50 meter per second. So again, we can use the energy conservation, right? Okay, so we'll have to use steam tables, and before proceeding, we can find the required value which we can require. First, we will require the enthalpy and the specific volume, because we have to calculate the area. For area, we will require density, and for density, we will require specific volume. So we can find the specific volume and enthalpy from the steam tables. Okay, so first at the inlet, we will check. Okay, use the steam tables. So at inlet, it is superheated steam. 500 degrees Celsius. And how much pressure? 4 megapascal pressure. Okay, 4 megapascal pressure and 500 degrees Celsius temperature. So at inlet, enthalpy is, from the table, it is 3446, and specific volume is 0.08644 meter cube per kg. So these are the values at inlet condition, and similarly you can find values at outlet. Okay, at outlet the quality is 92%, so it is saturated, so it should be in the saturated table. We have pressure, right? How much pressure? 30 kilopascal. 30 kilopascal. So we have outlet, H2 will be HF plus X into HFG, because it is into saturation region. So HF we can find from this. Okay, so HF is 289.27. Quality is 0.9, and HFG is 2335. 0.3 kilojoule per kg. Okay, so now you can calculate H2. Okay, so if you calculate this value, it comes out to be 2391.04 kilojoule per kg. Okay, actually it was 0.92, quality was 0.92, so we should multiply by 0.92. So it is coming out to be 2437.75 kilojoule per kg. Okay, and yes, so we have enthalpy at outlet as well. Okay, we have velocities at inlet, at outlet. Okay, so you can find the change in kinetic energy. Okay, At outlet velocity was 50 meter per second. At inlet velocity was 80 meter per second. And this value comes out to be, and since this is in meter per second and we want to convert this thing into kilojoule per kg, so you can divide by 1000, so you'll get values into kilojoule per kg. Okay. Okay. So and this value comes out to be, it will be negative minus, I'm getting minus 1.95 kilojoule per kg. If you are getting some different value, just let me know. Okay. So change in kinetic energy was very easy because velocities at both inlet and outlet was given. So you have just to find the difference. Okay. Another thing that we have to find is power output. Turbine is power producing device, right? So power output will be equal to change in this value, m v1 square by 2 plus h1 minus v2 square by 2. This is total energy, right? So change in total energy will be reflect as work output, right? Or power produced. Okay. So mass flow rate is given. Okay. And if you substitute all these values, you will find string to be mass flow rate is given 12 kilogram per second, and change in these velocities, this we have already found out. This is 1.95 kilojoule per kg plus H1 enthalpy at inlet was 3446 minus at outlet it is 2437.5 kilojoule per kg. Okay, so this thing will be found in kilojoule, right? Kilojoule per second. It is going out to be It is 12,125.4 kilowatt, or in terms of megawatt, you can write 12.12 megawatt. So this is the power produced. Okay. What else we have to find? We have to find turbine inlet area. For turbine inlet area, you can use the equation for mass flow rate, that is m dot is equal to rho a v, and mass flow rate is constant, so you can use this equation at inlet because velocity is given at inlet, mass flow rate is given. Okay, rho you can find from ideal gas equation, and a we have to find. Okay, so a, that is area at inlet, will be m dot v1. Small v is basically specific volume at inlet, and velocity v1, capital V1 is the velocity. So m dot is given, this is 12 kilogram per second. Okay, and specific volume we had found from steam table, and it is 0.08644. Okay, 0.0864 meter cube per kg, divided by velocity is already given, 80 meter per second. Okay, it is coming out to be 0.012966 meter square. So you can round off this value to 0.013 meter square. Okay, so this is what we had to calculate. Okay, inlet, turbine inlet area. Okay, power production we have find power output, and change in kinetic energy was very simple. So this is what we have to find in this question. Okay, so this was the last question. So in this session, what we have discussed some questions related to steam power system. We have discussed that there are two types of turbines: steam turbine and reaction turbine. Sorry, impulse turbine and reaction turbine. In impulse turbine, the expansion takes place only in nozzle, and there is no enthalpy change in rotor blades. Okay, and we have discussed that diffuser is just opposite of nozzle. So a diffuser slows down a fluid, and diffuser slows down a fluid flow, and it increases the static pressure. Okay, and we have discussed that degree of reaction is the total enthalpy change in rotor divided by total enthalpy change. Okay, so this fraction is the degree of reaction. Okay, so for the case of impulse turbine, there is no enthalpy change in rotor blade, so there is so the degree of reaction of an impulse turbine is 0. We have discussed that an economizer is a device which uses the heat of flue gases to preheat the heat water that will go into boiler. Okay, we discussed that condensation in condenser takes place at constant pressure and constant temperature because it is a phase change process. And Molia diagram, we have seen that Molia diagram are basically entropy enthalpy diagrams, and pressure constant pressure lines basically diverges in Molia diagram. Okay, we have discussed that in a reaction turbine, some part of enthalpy change takes place in the rotor blades. Okay, so at the inlet of the turbine you will find kinetic energy as well as pressure energy in case of reaction turbine. And superheating, that takes place at constant pressure but temperature increases. Okay, and because superheating is not a phase change process. Okay, and we discussed that there are two type of boiler, low pressure, there are two type of boiler here, fire tube boilers and water tube boilers. Fire tube boilers are basically simple, compact, more efficient, low total cost of ownership. And water tube boilers are high, they are quite precise and they can operate in high pressure condition and you will get high pressure. Okay, but obviously they will be little, costly. And in condenser we discussed that heat is dissipated mainly due to the convection. Okay, and condenser is some sort of heat exchanger. And nozzle, it converts the heat energy into kinetic energy. And if you neglect the velocity at inlet as compared to the outlet velocity, then you will get the change in enthalpy will appear as the increase in the kinetic energy. Okay, the exergy analysis we discussed that it is based on second law of thermodynamics, and we solved some questions where we had to find the degree of reaction, and we just use the simple formula for the degree of reaction. We solved some problems where the conditions at inlet and outlet was given, and using some tables, property tables for air or steam, whatever fluid is used, we can find the required properties, for example exact exit temperature or exit pressure. Okay, similarly we did the similar question for the turbine. The condition at inlet and outlet was given, so using the steam table, using the properties of steam, you can find whatever is required. Okay, so so that's all for today. Okay, thank you for attending. We will stop here and we will meet in the next session. Till then, take care. Thank you.